All right, let's pull back the curtain on the silent hero of your digital life, the operating system. I mean, it's this invisible force that makes everything on your computer, your tablet, and your phone just work.
I mean, think about it for a second. Every single time you open an app, save a file, or even just wiggle your mouse, there's this powerful manager working completely behind the scenes. So who is this hidden boss?
You know, the best way to get our heads around this is with an analogy. Picture your computer as this huge, high-tech hotel, and the operating system, the OS, is the general manager. It's in charge of absolutely everything, from the front desk and room service to security and maintenance. Its whole job is making sure that you, the guest, have a perfect experience.
So how do you actually check in? How do you tell this manager what you want? Well, it all starts the very moment you hit that power button.
This is basically the OS starting its shift for the day. There's this tiny little program, kind of like a night watchman, that wakes up the general manager, the main OS, from the hard drive, brings it to the front office, that's the computer's memory, and basically says, okay, you're in charge now. And just like that, the whole system is open for business.
So, once the OS is up and running, you've got to talk to it somehow. And you do that through the user interface, or UI. This is the front desk of our hotel. It's the place you go to make all your requests, whether you're typing out a command or just clicking on an icon.
And there are really two main kinds of front desks. On one hand, you've got the command line interface, the CLI. This is like talking to a very literal text-only concierge. It's super powerful, but you have to know the exact commands. Then you have the Graphical User Interface, or GUI, which is what most of us use every day, that friendly visual world of icons and windows and pointers. But what's really interesting is that most modern systems, like Windows and macOS, they aren't just one or the other. They give you this beautiful GUI, but they also have that powerful CLI working just underneath the surface if you need it.
Okay, so you've walked up to the front desk and made a request. Let's say you want to copy a file from one folder to another. What happens next? This is where the OS really starts to earn its keep.
The OS provides this huge suite of services, kind of like all the different departments in our hotel. You've got program execution, which is like the events team launching a party. File management, that's the records department. I/O operations handles all the external gear, printers, cameras, and of course, you have security guards at every single door.
Now here is the crucial point. An application, like your file manager, can't just do things on its own. It's not allowed to directly touch the hardware or any of the critical system resources. Instead, it has to submit a formal work order to the OS, and this work order has a name. It's called a system call.
So when you just drag and drop a file, what you're really kicking off is this incredibly rapid-fire sequence of system calls. The app sends a call to open the first file, then another to create the new one. Then it goes into this loop sending read calls and write calls over and over until the job is done. And finally, it sends a couple of calls to close both files. All of this happens in a fraction of a second, completely invisible to you. It's amazing.
So we've seen what the OS does, but how is it all organized? Let's take a look at the architect's plan and see how these incredibly complex systems are actually put together.
Just like hotels, not all operating systems are structured the same way. Some are designed for pure, raw speed. Others are built for maximum security, or maybe flexibility. This internal architecture, its management philosophy, if you will, is really a game of trade-offs.
Early systems like MS-DOS had a very simple structure. Think of a small motel where the owner is also running the front desk, cleaning the rooms, and doing the accounting. Everything was just bundled together. It was pretty efficient for its size, but not very secure or easy to manage as things started to get more complex.
So then we got a more sophisticated design, the layered approach. This is like a proper hotel with distinct floors. The user interface, that's the top floor, the penthouse. Below that, application services, and way down in the basement, you have the hardware control. And here's the golden rule. Each layer can only request services from the layer that's directly beneath it. This creates a really clean, organized, and much more manageable structure.
And then there's the microkernel approach. In this hotel, the general manager, the kernel, does as little as possible. It only handles the absolute most critical tasks, like letting different parts of the system talk to each other. Everything else, file management, device drivers, is run as a separate, non-essential service. So if the laundry service has a problem, it doesn't shut down the entire hotel. That separation makes the whole system incredibly reliable and secure. And this table just lays it all out perfectly. It's all about those trade-offs, right? A simple structure is fast because there's no overhead, but it's not flexible or secure.
The layered approach adds some overhead, but you gain modularity. And the microkernel? It's the most secure and flexible of the bunch, but all that messaging back and forth between services can slow things down. There's just no single perfect answer. Building these systems is just mind-bogglingly complex. As the computer science legend Brian Kernighan once said, debugging is twice as hard as writing the code in the first place. That's why these structures matter so much. The simplicity of a layered or microkernel approach isn't just about being elegant. It's about building something that we humans can actually understand and fix when things inevitably go wrong.
So how does all of this theory actually apply to that little supercomputer you carry around in your pocket? Let's bring it all together and look at the devices we use every single day.
The reality is, modern operating systems like Windows, iOS, and Android aren't pure examples of any single one of these structures. They're hybrids. They cleverly take the best ideas from each approach: the raw speed of a simple structure, the organization of layers, and the security of a microkernel to create a really balanced system that gives us the best of all worlds. Take iOS, for instance. At its very core is a hybrid kernel, combining a secure microkernel with some really reliable components from older systems. This gives it both stability and security. And then, built on top of that solid foundation, is a very clear layered structure, with your apps sitting at the very top, all supported by those powerful core functions running deep underneath.
And Android? Well, it follows a pretty similar blueprint. It's built on the powerful and famously stable Linux kernel, which is a total workhorse known for its reliability. It also uses a layered stack, with your apps right there on top and that kernel at the bottom managing all the hardware. It's this clever hybrid engineering that makes both of these tiny pocket computers so incredibly powerful.
So from a simple click to a silent symphony of system calls, layers, and kernel services, it all just happens in the blink of an eye. The operating system is truly the unsung hero, the hidden boss that makes our digital lives possible. Maybe the next time you use your phone, you'll think about that invisible manager, that complex orchestra working flawlessly in the background just for you.